What could I tell you about triangles that hasn't been said before? Triangles have three sides, so you can set them on a base on any of the three sides. You can also hinge a triangle on its base to flip it over. You can also spin the base of a triangle to flip it over. Here I'm showing you all the different orientations of a triangle. It's all the same triangle. I'm showing you the process slowly. Each orientation is just another flip. There are three sides to a triangle, so you can set any triangle on a base three ways. You can turn it over and set it on the base three other ways. Or you can flip it down and have it hang from the base. The total is 12 orientations of a triangle, where one of the sides is horizontal. When all the triangle orientations are laid out, we see that it's in a symmetric pattern. I fix the base of this triangle and set all the triangles on that base. These triangles have the same size of base, so they don't need to be scaled. This triangle has a much longer base, so we'll scale it using a parallel line to one of the sides. It provides us with a similar triangle. Similar triangles are similar because they scale up to be the exact same size and angles. Now I can put the triangle on the same base. I continue for the rest of the triangles, not showing you all the work and stuff. Now, I didn't do it too well here, so I'm going to do a little adjustment. There. Fixing the triangles shows you what it looks like. Here I made a triangle machine. It's a rubber band with two tacks. I used a necklace so that my finger wouldn't get in the picture too much. You can imagine that all triangles could be created using this device if the rubber band was super elastic. Here I drew some lines on the image more clearly to show you where the special triangles lie. Do you see it? Do you see it? Here's an equilateral triangle. Here I'll show you. These are, all the blue are acute, and all the white area is obtuse. on the green line is on the orange line are the right triangles. On the green line is isosceles triangles. You see that the triangle has two sides that are equal to the radius of the same triangle. So it'll always have two sides and be isosceles. The isosceles triangle also has a line going down the center of the image. And it has it on the bottom too. So what is this? What is this diagram? Well, I started thinking about it, and it has symmetry. The similar triangles, as I showed you, those 12 triangles that fit together, sit inside those areas separately in a strange and move in strange patterns. It's as if they're reflected in strange ways, and my early drawings showed that there was something strange going on that I couldn't figure out. And so I wrote a computer program to help me figure things out. This shows the 12 dots of a triangle. Each frame is a different triangle that is nearby. And 11 other dots are shown for the similar triangle. One dot represents a triangle that I am varying its point in a straight line. The other dots represent the triangles that are similar to this triangle within the image. What we see is that a straight line creates circular patterns for the other triangles. I came to the realization that it was running out to infinity because it was essentially on some kind of spherical surface. And when I thought of it that way, it suddenly became a very symmetric object. Here you see on the top it has 3 or 6-fold symmetry, and then it's also split in the side. It looks like an orange or the Earth split at the equator, with the longitudinal lines only being 6, and the latitude lines only being at the equator. It's quite simple. It's 12 wedges, 12 somewhat like half wedges, 12 wedges of a complete sphere, or 6 wedges of a sphere cut in half. So I decided to draw this image onto a sphere, but I couldn't find anything, and then I had a light bulb idea. I would cut masking tape onto a light bulb. The reason I wanted to do this is because I wanted to show the projective geometry. The projective geometry comes from projecting the image from the inside to the outside along a plane, and I thought maybe I could do this with a light bulb. However, shortly after I began, I realized that the light bulb couldn't be set in the center, rather it needed to be set at the top. So the light bulb itself was not going to work. However, you can see as the shadow pattern shows that something is occurring, something very interesting. And obviously I created this with intent in mind, and the intent was to show a similar pattern. You can't really see it like this, so I thought of another idea and went to the dollar store and grabbed a laser pointer. From here I could illuminate the top of the object while sitting it in the orientation that I wanted on the ground and create the shadow pattern that I desired to see. I tried other methods, and this one seemed to work best. So it allowed me to see the shadow on the ground, and the pattern was remarkably similar, as I expected, to the pattern which I seen drawn out by the triangles when marking the spot of special triangles. I felt it meant that this image really was the image that we see on the flat piece of paper, really was an extension of an extra dimensional object. I checked out this symmetry in Wikipedia, and I believe what I found is that it is a type of symmetry, octahedral symmetry. It is, I think, called dihedral or something. Anyhow, I wanted to demonstrate it, so I cut up this piece of plastic that was covering the ping pong balls I purchased, and into 1/6 of half a sphere, and then I put it into a wedge mirror in my bathroom and pointed the laser pointer at its surface in order to demonstrate the symmetry. I aligned the symmetry by looking in the mirrors and lining up until I could see 3 wedge segments before the third mirror matched the one I was holding in alignment into the reflection. That created 6-fold symmetry on the top, and then I put a mirror on the bottom to create the bottom symmetry. I put the piece of plastic that was cut to be a wedge of approximately the size in the edge, in the wedge, on top of the mirror. And then I projected the laser onto it. The objective was to get the laser to sit on the top of the sphere surface, but also be able to see through the sphere. Unfortunately, the mirrors are not close together, and the reflections cause too much distraction to see what is actually going on. So here I took a solid object instead. Now you can't see the backside of the object, but you have to imagine you're only seeing half of it. And so these 3 points you see are joined up by 3 more on the backside. I could kind of see it with my eye, but you can hardly see it with the camera angle here. But you could see that there were 6 points that joined up into 3s as they grouped together along their symmetry points. So there was 6 or 3-fold symmetry on the top, and then at the base you will see it joins into 4. That's the 4-fold symmetry where the equator meets each of the longitudinal lines of the sphere. So it has a strange 3 or 6-fold symmetry on the top and a 4-fold symmetry on the side. I think it's called 2,3 symmetry, but I'm not sure. So that's it. I show you how anybody, when fixing 2 points of a triangle, can create this image quite easily, just by considering, hey, where are the important triangles? And then from this, you see that it's actually a projection from an image on a sphere down to a plane, a flat surface, where you're drawing that image out. So I think it was Plato or Socrates said that everything is a shadow on a wall. Well, maybe when you draw a triangle, like maybe you're not really, or when you recognize a triangle, maybe it really is a shadow of some upper dimensional or some greater understanding of the object, and you're just seeing the projected shadow.